Hey everyone, in this video I'm going to go over the example from video 243 for RC circuits discharging a capacitor. In this example we have, let me turn my video back on here. In this example we have discharging a capacitor. We have the switch in the circuit has been in position A for a long time. So the capacitor is fully charged, and then the switch is changed to position B at time 0. So what in the world does that mean? Okay, what this means when the switch is at position A, this is open here, that means there's no current flowing through it. It's as though this part of the circuit doesn't even exist. If this part of the circuit doesn't even exist, that means that the capacitor is directly connected to the battery, and it's been connected for a long time. It's going to be fully charged. That's what this means. The capacitor is fully charged. That means that it has the full 9 volts from the battery. And then the switch is changed to position B at time 0. So if we draw a picture for this, we now have the capacitor, which has the full 9 volts on it, is now connected at B. So this is closed here. We have our resistor, and we have our capacitor. So now that the capacitor is fully charged, it is now going to discharge through the resistor. What is the current in the circuit immediately after the switch is closed? That's the first question. So what I'd like you to do is write down the equation that is related to this. Okay, did you get it? You had two choices, right? You had I naught is V naught over R, or you had I as a function of t is equal to I naught e to the negative t over RC. Which one did you pick? Immediately after the switch is closed, that means the initial current when the capacitor is just starting to discharge. So we can just find the initial current using V naught over R. So I naught equals the initial voltage, which is 9 volts, because it was fully charged, and the resistance is 10 ohms. So 0.9 amps. That is the initial current through the circuit. What about part B? What is the current in the circuit 25 microseconds later? This is when we use the other equation, because this equation gives us the current at any other time. Now technically, if you use this equation to find the initial current, then the time would be 0, and anything that has an exponent to the 0 is equal to 1. So if you do e to the negative 0, then all of this would cross out to 1, and you have that initial current is I naught. You see that this equation would be very helpful. So it's helpful for any time not equal to 0. Okay, so the time that we're looking for is 25 microseconds. 25 times 10 to negative 6 seconds. So why don't you try plugging it into this equation just to make sure that you know how to use your calculator and how this equation works. This e is the exponential. It's not the same thing as a double e key. That means times 10 to the in your calculator. It is not that. This is an exponential function, e. You may see it in your calculator, e to the x perhaps. Okay, so try it out, and all we're doing is plugging in that the current at this time is going to be I naught, which is 0.9 amps, times e to the negative time, which is 25 times 10 to the negative 6, divided by R times C. Make sure R and C are in the denominator. R is 10 ohms, and C is 1 microfarad. 1 times 10 to the negative 6. So before trying to plug in all of this stuff in a calculator, you can actually see that the 10 to the negative 6 actually cancels out. So you're left with 0.9 e to the negative 25 over 10. So plug that into your calculator, and you're going to get 0.074 amps. So if we were to visualize this current through this circuit as a function of time, we know that it looks like this exponential function. We know that the initial current here is going to be I naught, that's the 0.9 amps. And then what we're saying is at this time here, this is not to scale, but let's say that this time right here is 25 microseconds. At this time, because this is t on the x-axis here, at 25 microseconds, how much current is there? Well, that number should be 0.074 amps. So that is an example for using this equation. In the next video, we're going to be charging capacitors and doing more examples with those. See you then.